Hey everyone, this is John Buck back with another array signal processing video. This is video 2 in the series on k-omega beamforming. So if you haven't already seen the first one with the overview, I'd ask you to go back and look at that first. And in this one we're talking about the practical issue that when we get real data, it's almost always sampled in space and time. In the previous video we talked about, well, in the perfect ideal world, if we could measure all of time as a continuous variable t, and all the z-axis where our array is aligned as a continuous value z, and had all those values, what we would do with them. But in practice, we often don't have that, right? As we've seen all semester in this class, we're going to stay with the same assumption tonight that we have a uniform line array on the z-axis where the elements are spaced every d meters apart. And then I have some plane wave coming in, propagating in this direction, coming in where this makes some angle theta. Go back to the other drawing. Some angle theta with the axis, right? And so theta relates to k sub z. We've seen earlier this semester for the incoming plane wave, we write this as minus 2 pi over lambda times cos theta. Or as we'll be using a lot more, we can say, well, 2 pi over lambda, we can also write that as omega over c times cosine of theta. We'll be using this formula a lot tonight. And so by having this uniform line array, we've taken something that's continuous on the z-axis and sampled in space. And so we know that has implications, right? That sampling every d in space means that I make copies of x of k every 2 pi over d, right? This is where we have to worry about spatial aliasing. If these x of k is too wide, these copies will overlap. And then in a modern data acquisition system, we are pretty much always going and taking these continuous signals coming off our antenna or our hydrophone, and then sampling them in time, right? So that I'll get, say, x of sub 0 of n here is a discrete time signal that are samples of x of t taken every capital T seconds, where t is 1 over the sampling frequency fs, right? But this would be like x0 of nt, this continuous time signal sampled every nt, and so on up the line for my whole array. So I've now got data that's sampled in space by a uniform line array, sampled in time every t seconds. Right, so just all of them sampled together. And so sampling in every d in space puts copies in one hand. On the other hand, we know from our DSP class, this samples in time put copies every 2 pi over t in omega. So we need to make sure we don't have aliasing in space or time, that we're sampling fast enough in time to avoid aliasing in omega, and that we're sampling fast enough in, or right, close enough in space to avoid making aliasing in x of k and to interpret these graphs. And when we do it, we'll see we have to use computational DSP algorithms we'll talk about in class. But our goal is to basically Fourier transform this sample data in both time and space, and then make a picture or estimate a plot of what it looks like. So let me show you sort of a notional graph of how we show this. So when we make this plot, we're going to have this will be our kz axis in this dimension, our omega axis in this dimension. And because of the sampling and concerns about aliasing, we're generally going to limit this. Ooh, wrong button. Sorry. And so we might say, well, actually, let me give myself a little more space. I might stop here and say if this is pi over d will be between plus and minus pi over d. And remember, kz, this is the zero part. This is kz greater than 0 and kz less than 0 down here. Now, we have to be a little careful about this because of our convention for defining the plane wave, like in Van Trees. If this is omega over c, or it's minus omega over c times cos theta. So when theta is equal to 0, I get minus omega over c, right? So I get, it sort of flipped the axis. So theta equals 0 is down this way. Theta equals 180 or pi is up here. And this is right at k equals 0. That's still broadside. So pi by 2 is here. So I have that going on. And then I also have to worry about aliasing here, right? And we know, I'll make myself a little more room here. This will be at pi over t. We want to go out to pi over t because it repeats every 2 pi over t. Right, so we know I've got aliasing and frequency like this. And the other thing we'll take advantage of, well, what we're going to do is we're going to plot the magnitude of that time and space Fourier transform squared. As you know, and here we'll just be doing like grayscale. On MATLAB we can do it as a color scale. So it's sort of like showing the energy in terms of at each point on the plot. But we also know the other thing we'll take advantage of is since the original signal in t and z is real, we know we have even symmetry in the magnitude of omega. Move that down where there's a little more room for it on the side. That tells us that the magnitude of omega kz is the same for plus or minus omega. Right, the magnitude is an even function in omega for real signals. So we're only going to just plot the omega greater than 0 part. And so sort of our region of interest, to avoid aliasing, is this box here. Anything that leaves this box sort of wraps around from one side or the other. And so there's some important boundaries on this plot we want to set out with first. Well, the first thing to consider is if I look at this line, a line of constant theta, if I hold constant bearing, where does that appear on this graph? Well, that means cos theta is a constant, right? If theta is constant, so is its cosine. And so we can say this line, the kz is the vertical axis. If I rearrange the terms a little bit here, I can say this is minus cos theta over c times omega. So if I think of omega as the x-axis, or the horizontal axis, kz is the vertical axis, a line of constant theta is a line of constant slope on this graph. So for example, at forward end fire, when theta is 0, I have a slope of minus 1 over c. And so it's actually an important issue is where does this fall on the graph? And similarly, at the other extreme, at 180, I have this other line. So this line here is the theta equals 0 line, right, with slope minus 1 over c. And this would be the theta equals pi line, or rear end fire, with the slope 1 over c. And it's an important point, when they reach these limits of plus or minus pi over d, that's actually the design frequency for the signal. So it may or may not be related to twice the sampling frequency. In fact, it might be a lot less. But the region, the visible region, remember we defined the visible region. I'm going to have to hop to a new page and then come back just to keep this graph. Right, so remember we said in general the visible region for a narrowband beamformer is that I have minus omega over c less than or equal to kz less than or equal to omega over c. And And so I'm in between those two. So the width of that and the vertical axis gets wider as omega gets bigger. Right, so the visible region is in here. So the other thing we might do is we're going to go color the part that's not the visible region, saying everything up here is actually not a propagating plane wave. Right, so this red part here is the not visible region, or it's not the visible region. So anywhere before this, for a line of, let me pick a different color here. For the line of constant theta, got a line drawing, may as well use it. Right, this will be some angle here, and actually because it's kz omega over minus cos theta over c is positive the way I've drawn it here. This must be some angle more than pi over 2. So this is a line, some theta greater than pi over 2. Any signal coming from that bearing will appear on this line. Now there may not, depending on how much bandwidth there might be more or less of it on the line here. And the other thing is worth working out is this point here where, what happens when the line hits that point here. So let's do that in the next, go back to my scrap pad on the next page. So we're looking at the case where I've got, well, omega's been increasing with omega over c, and that point was equal to pi over d. Well, at this point, it's worth maybe going back to, remember the other way we could write the magnitude of the wave vector is 2 pi over lambda. So I can solve these two end ones by taking the reciprocal on both sides and factoring out. If I take the reciprocal first, I'll lambda over 2 pi is d over pi. And so canceling the pi's, that tells us that the point where I hit just before I start aliasing in space is what we would expect. That's the frequency where d is equal to lambda over 2. So whatever fixed d I have on the array, that's the point where the wavelength, that graphically represents the frequency where it's lambda over 2. Will be this point here where I hit this axis. And so this sort of gives us a new perspective on why when I know things are limited near broadside, I can go to higher frequencies, because that means if I'm near broadside, that angle is represented by a slope that's not as steep, and so I can go to a higher frequency until I hit this pi over d limit for aliasing, right before I start to roll into the next copy up here that I'll have additional copies. Okay, so I guess the last thing we'd mention is, so what does a plane wave look like on this graph? If I have a plane wave, well, it'll be a point like this, where it's on some line. Right, this line is determined by its angle. That tells me what kz is, and this is the omega naught. So this would be my plane wave at omega naught, and the y-axis would be k naught. And then I could solve this equation here to find the angle if I wanted to. I say, well, I've got k naught for that plane wave, narrowband plane wave. K naught is minus omega over c cos theta. So I could take this and say, well, I could read k naught off the graph, have minus k naught over c. I could read omega naught off the graph, and this would be equal to cos theta. And so I could figure out the angle for that point, that plane wave. I'd get omega naught from looking at the graph, and then convert k back by saying, well, I've got the arc cosine of minus k naught c over omega naught. And as long as I'm in the visible region, this argument will be between plus or minus 1, and theta is a well-defined angle. Okay, so we'll talk some more about interpreting other versions of this and other kinds of signals tomorrow in class. But I'm going to stop here for now. The video is long enough, and get these uploaded so people can watch them before class. All right, so that's sort of some introduction to k-omega beamforming. We'll talk more tomorrow about computational issues using the discrete Fourier transform. And we'll also talk about, or I guess the one thing to remember from this then is that we have the lines of constant theta show up as straight lines of a given slope on this graph. And if I put the lines down for theta equals 0 and pi or 180, I get the limits of the visible region, and anything outside those lines actually cannot propagate as a plane wave. It won't satisfy the wave equation we saw at the start of the semester. All right, that's all for this time. I'll talk to you later.